the first thing I'm going to do is run through these questions that we covered from our last lesson. So what we've been looking at so far is what the derivative is and what it does. So we've looked at how to differentiate rational functions. So rational functions just have a power that is either a positive number, a negative number, or a fractional number. Why have we differentiated? We've focused on differentiating so far just to find the gradient as a means of calculating the gradient. So that's what this question is about. If my rule is 2x squared plus 2, we've called it h of x. This is what the graph looks like. We should know that that's a parabola that's been translated 2 units up. When I find the derivative, it is important that you actually use the correct notation. So I've kind of been banging on about this a little bit. When I actually go through that process of differentiating, it is important that I show that I have differentiated using the correct notation. My derivative of h of x will be equal to 4x. And then we're being asked to calculate the slope. What's another word for slope? Gradient. We're being asked to calculate the gradient at these points when x equals -3, when x equals 0, when x equals 3, and when x equals 100. To do that, all I need to do is substitute those x values into my gradient function. So this is my gradient function. It tells me what the gradient is equal to at any value of x. So the gradient function. Given that the question talks about the slope, I guess we could have called it the slope function. All right, but gradient, slope, same thing. Substitute in 3, we get 12. Substitute in -3, you would get -12. That makes sense. We've got this graph here. When x equals 3, it's saying when x equals -3, I'm on the negative x-axis. When x equals -3, the slope of the graph would be going down. It should have a negative gradient. When x equals +3, the slope of the graph would be going up. And it makes sense because the parabola is symmetrical. One is -12 and one is +12. Question?
The function is 2x squared plus 2.
Yes.
If it was 2x squared plus 2 plus 3x, would 2 still equal 0?
The 2 part would still equal 0 even if the order changed. Correct. Any constant, when I differentiate a constant, it always goes away. It equals 0. Okay, substitute in 0 in between the 3's. What do you think the gradient's going to get? 0. How do you know? Now, the gradient, when I substitute in 0, this would be 4 times 0, which just equals 0. But what I hoped you might have recognised, if the gradient function actually is calculating the slope, if the derivative is calculating the gradient, you should hopefully know that when I calculate the gradient at that point there, it's just going to equal 0. It's a stationary point, it's flat. Or the turning point, the gradient at the turning point is going to be equal to 0. And then what do we expect is going to happen when I substitute in a really large x value, 100, all the way over here somewhere? What would the gradient be at that point? It would be 400. And that makes sense. It should be a large positive number. A large positive number. All right, they are the answers to our entry. Right. So what we're going to look at today is a little bit more about, well, why are we doing the gradient? Why are we doing the derivative? We have explained that derivatives can calculate the gradient for us. They are also a really powerful unit or a really powerful measurement for analysing graphs. Gradients are rates of change, okay? So finding out the rate that something is changing can be really powerful in modelling and research and analysing functions and data. So we're going to look at when you can actually differentiate today. But before we can look at when you can differentiate, the first thing you need to know is what a continuous function is. And you might want to add this to your summary journal under a heading about continuous functions. There's going to be a few notes here. You can go back to these slides to copy notes and nice pretty pictures if you missed anything now. But we're going to actually start talking about continuous functions. Not a formal definition. This is not a formal definition of a continuous function, but a continuous function is basically a graph that we can draw without lifting our pen off the paper. This is an example of a continuous function. This would be a quartic. Quartics have a power of 4. Polynomials that have a power of 4. So this would be a quartic. Discuss with the person beside you for the next 30 seconds, how could this be made discontinuous? What would a discontinuous graph look like? Discuss, 30 seconds, go. So as I moved around the room, a couple of things I heard was truncuses and hyperbolas. I couldn't draw truncuses and hyperbolas without lifting my pen off the paper because they have an asymptote. There are 3 main types of discontinuity. The first type, I can have holes in graphs. Now that might be strange to say that I've got a hole in the graph. What on earth does a hole in the graph look like? Here's an example of a hole in the graph. If I had x squared divided by x plus 1, what numbers won't work for this graph? -1, how come? Because you'd be dividing by 0. If I actually graphed this on my calculator, it would look like it was a nice straight linear line. I'm not 100% sure that that's a linear graph, except at the point where x equals -1, I can't substitute x equals -1 into the graph. So it creates a little hole in the graph, a little point where the graph is undefined. So sketch it on your CAS calculator, it looks like it's just a linear line. But if you actually scroll through the points and trace the points, you'll find that when you get to x equals -1, it says it's undefined. The reason it's undefined is because you can't divide by 0. So we can have holes in the graph, points that are undefined. We can have graphs that actually have a jump. These are usually caused by hybrid functions. Remember when we did our first investigation task at the start of the year and I asked you to draw a picture and you had to create graphs and we had specific endpoints so that you could create the picture. You created a whole heap of non-continuous points along the graph. You created all of these points that had little jumps. Non-continuous graphs when we have jumps. These are usually hybrid functions. We'll have a look at some hybrid functions before the end of today. And then as Nyasha and Brigitte said, if we've got a hyperbola or we have a truncus, when we have vertical asymptotes create a jump in the graph, so the graph would be non-continuous. All right, so as I said, the idea of lifting your pen off the paper is not a formal definition of continuity. For a formal definition of continuity, what we actually need is for the graph to basically be approaching the same value from the left-hand side of the graph and from the right-hand side of the graph. So for a formal definition, there is one in your textbook, I've forgotten exactly what it is, but if f of x equals the value a, yes. Continuous functions, yes. So if some value of x, if the value of x is equal to a, and when I approach that value from the left-hand side, from the left-hand side's the negative side, it must also equal a. And as I approach that value from the right-hand side, it must also equal a. What on earth am I talking about? Here's the graph. Oh, that's a horrible green. I'm sure some of you can't see that. Here's the graph of a parabola. Correct? Now, If I said, is this graph continuous at x equals 2? Is this graph continuous at x equals 2? We know for a parabola, we've been drawing these all year, we draw one straight line. In fact, I told you don't do little hairy dog graphs, do it in one continuous line. We know that graph is continuous. But what does all of this mean? Okay, this is the graph of f of x equals x squared. So let's first find out what is f of x equal to at the point x equals 2. So substitute 2 into the equation, we get 2 squared. F of 2 equals 4. Right? So my a value is 4. Then, what this first part is saying is, okay, is that the same if I'm tracing my graph from the left-hand side and I'm going along this graph towards the point x equals 2, what is the limit that the graph is approaching? As this approaches x equals 2, is my graph approaching the value of 4? Yes, it is. Like, we can see it's actually going to that point. All right? So we can say the limit as x approaches 2 from the negative side of f of x, the limit as x approaches 2 from the negative side, it's also equal to 4. Seems pretty stock standard, self-explanatory. And then same, if we now find the limit from the right-hand side. So as we're going this way and I approach 2 from the right-hand side of the graph, am I going to the same spot? Yes, of course I am. Because we know this graph is continuous. So if these three things occur, therefore, f of x is continuous at x equals 2. All right, well, let's consider a different type of graph. Let's have a look at this one. There's a bit going on here. This is what we call a hybrid function. This is what we did with our investigation task. We did a whole series of different equations and we set a domain for those equations. Let's have a look at this graph. Okay, when I have this function that looks like this, we did talk briefly about hybrid functions earlier in the year, but not at depth, so we're sort of covering it a little bit more now. This is base functions in 1. If I wanted to sketch that graph, I would start by just sketching the graph of 3x. Graph of 3x, it is a linear graph that's been made steeper because of the 3. It would go like this. And because it doesn't have, it's like plus 0, remember this is the y-intercept, I know it goes through 0, 0. So this graph looks like that, that's 3x. Except I only want to use this graph when x is greater than or equal to 0. So I don't want to use that graph for any of these values where x is less than 0. And because it is equal to, I need to put the endpoint as a closed circle. All right, there's my graph. Now let's graph this one. It's still a linear graph. It's in the form y equals mx plus c. The c value is plus 2. So I know my y-intercept is going to be positive 2. And it has a negative gradient. It won't be as steep as the 3, but it is going down, so it's going to look something like that. And I only use this graph when x is less than 0. Not equal to it though, so that actually has to be an open circle. Speaking of continuity, I need to understand, is this continuous? Is this a continuous graph? No. Where's it not continuous? Be more specific. In the middle. How else could we describe where it's not continuous? Say it out loud, Kane. You might have said it right. How else could I explain where it's not continuous? After its endpoint, I'm looking for a little bit more detail, a little bit more specific. On the y-axis, how else can I describe the y-axis? You're getting closer. Thank you, Alice. That is perfect. Discontinuous at x equals 0. Okay, it's discontinuous at this point where x equals 0. We can see that visually. Now, if we wanted to try and describe that formally, what we would do is we would find out the value. We want to prove that it's discontinuous at x equals 0. So let's find out the value of the function at x equals 0. When x equals 0, am I using this part of the graph or am I using this part? The top one, how come? The bottom one is only less than 0, not equal to it. The top one is when x is greater than 0 or equal to it. So if I want to calculate f of 0, I have to substitute 0 into the rule 3x. So I'm going to make it 3 times 0, which equals 0. So when I substitute f of x into the equation, I get 0. Okay, now let's find the limit as x approaches 0 from the negative side, from the left-hand side. So the limit as x approaches 0 from the left-hand side. So as I trace this graph from the left-hand side, tracing this graph from the left-hand side, what is the graph approaching at 0? What value does it get to there? 2, because that was the y-intercept. Okay? I'm proving, so now I'm formally proving that it's not continuous. I am now doing a formal proof and using limit statements to explain why it's not continuous. All right? We know it's not continuous, but you won't get full marks if you just write discontinuous at this value. You need to show why it's not continuous. Okay? Give me a minute, I'll do the next part and then I'll answer your question. Now we check from the other side, the limit as x approaches 0 from the positive side of the function. So now, as I trace my graph from the positive side of the function back towards 0, what's the limit of the graph? What's the value that I'm approaching? I'm approaching 0. So now, for it to be continuous, all of these values would have to be the same. Are they all the same? No. So what I actually state is I then go to a statement and I say the limit as x approaches 0 from the negative side does not equal the limit as x approaches 0 from the positive side. Therefore, f of x is discontinuous at x equals 0. Now, if it was a test and this is freaking you out, just write that. That's like our first stage. I can determine the concept, I understand the concept of continuity. All right? But you haven't formally stated it, so you haven't met this success criteria of formally stating it if you just do that. This is how we do a formal proof of continuity. All right, formal proof of continuity. And when I do a formal proof, I state why it's discontinuous, and then I have a therefore statement. So my reason and what it means. Reason, what it means. If a graph is discontinuous, you cannot differentiate at that point. If a graph is discontinuous, then the rate of change does not exist at that point. The function is not differentiable at points of discontinuity. Functions are not differentiable at points of discontinuity. So this graph, these are all points of discontinuity. All of those little jumps are all points of discontinuity. So can I differentiate at 0? Can I differentiate at 1? Can I differentiate at 2? Can I differentiate at 1.5? At this point at 1.5, the derivative exists. It's in the middle of my graph. There's a line there. The derivative exists at 1.5. The derivative does not exist at 2. The derivative does not exist at 1. Does the derivative exist at x equals 0? No, because it's discontinuous at this point. Does the derivative exist at x equals negative 2? At x equals negative 3? Because it's just on the line. Does the derivative exist at x equals 4? Yes, it's on the line. There are a couple of extra rules about when functions' derivatives don't exist. Here, we have a vertical slope, straight up and down. What's the gradient of a vertical line? Undefined. The gradient of a vertical line is undefined. And if the derivative finds the gradient, then the gradient's undefined, the derivative's undefined. The derivative is undefined at vertical lines. Okay? Derivatives are undefined at vertical lines. And there's one more. These are what I call pointy points. All right? There's not a smooth transition. Pointy points. If we have a pointy points occur with often with modulus graphs or absolute value functions, okay? Derivatives don't exist at pointy points, and it has to do with how that rate of change actually transitions from being a positive value to a negative value instantaneously without having a smooth 0 in between. Derivatives do not exist at pointy points. Good way to picture this, if you zoomed in, would it make a nice straight line? Or hence like becoming a nice smooth gradient transition? Or does the graph have a pointy point? If I zoomed in, does it still look exactly the same? Is it just still pointy? Okay. Recap. Derivatives don't exist at discontinuity. They don't exist at vertical points. And they don't exist at pointy points. Okay, we're going to do an example, but before I go through it and have you just listening, you need to have a chance to do something more active. So I would like you to try and draw these two graphs, sketch these two graphs before we even start. So we're going to, for the following function, state the values for which the derivative is defined, find the derivative for this set of values, and sketch the graph of f dash of x. Sketch the derivative function. Before we sketch the derivative function, we're just going to actually draw the graph. All right. Okay, so we've got discontinuous at x equals 1. So when x equals 1, what does that rule equal? It'd be 1 squared plus 2 times 1, which is 2 plus another 1. So 1 plus 2 plus 1. And ignore the fact that it's at the level of 3 because it's not quite right. Okay, it's discontinuous. Where's it discontinuous? It's discontinuous at x equals 1. So my graph is discontinuous at x equals 1. Does the derivative exist there? No, it does not. So the derivative does not exist at this point. So what I'm going to do now, state the values for which the derivative is defined. So the derivative is, Derivative is defined for everything that is less than 1 and the derivative is defined for everything that is greater than 1, but the derivative is not defined at x equals 1. So how could I write that? Yeah, one of those weird little things that we've learnt about. Derivative is defined for x being an element of R excluding 1. That's one way. X is an element of R, all real numbers, except for at 1. I'm not sure what these ones are, but I think I know what you're talking about. I could say the derivative exists. Oh, yeah. So I could say for x less than 1 or x greater than 1. And then I can be fancy and I can put that in a set notation like that. So this says the derivative is defined for the set of values, curly brackets for a set of values. The set of values that includes x such that x is greater than 1 or x is less than 1 or x is greater than 1. I could do it that way. How else could I do this? Negative infinity up until 1 or 1 to infinity. Because I want you to show maths notation. You're supposed to know how to do this.
So if you were going to write it in a sentence, you won't get one.
There's probably a good question. It depends how well you write it.
Like just simple, like what you said.
Yeah. When I say it depends how well you write it, it kind of actually depends on what the marking scheme is that's been set up. So if it's like a 2-mark question, then they might be asking for you to do it correctly and to show correct notation. If it's a 1-mark question, they might be asking for you to just write it. It could be a 1-mark question, but they're actually specifically looking for some correct notation before they give it as correct. And you don't always know that, so it's better to err on the side of caution and do that. Okay. We've stated the values for when the derivative is defined. How do we find the function f dash of x? How do we find the gradient function? We're going to differentiate that. How are we going to differentiate that? The answer is really simple. I differentiate the first part. Say it again. Missed a bit. 2x plus 2. Okay, now this 2x plus 2, we're going to use that for all of the values of x that are greater than 1. The gradient, we need to find the derivative of this function, the derivative of that, to calculate the gradient for all values when x is greater than 1. So that's going to be used for x greater than 1. Notice the equal to sign's gone. It's not greater than or equal to 1 because the derivative doesn't exist at 1. And then we're going to differentiate that. What's the derivative of that one? Just negative 2. And we're going to use that as my gradient for x less than 1. So my gradient function also becomes a hybrid function that's got 2 parts. And I just simply differentiate the first one, differentiate the second one, and then play around with my domain to make it fit for when it's defined. Lots of notation going on, but there's if you stop and think about what you're actually doing, it's really exactly the same thing for a singular function. We're just going into a little bit more depth and thinking about when does it work, when it doesn't work, which is our success criteria. I can determine when the derivative exists. So we're looking at how do I actually know when the derivative exists for some of these extra funky graphs and functions that we've looked at. Okay, last thing. So for the function with the following rules, state the values of which the derivative is defined. Tick. Find f dash of x, find the derivative function for this set of values. Tick. Last thing, sketch the graph of y equals the derivative function. We've sketched the graph of f of x. We haven't sketched the graph of the derivative. How do we sketch the graph of the derivative? Well, let's start with this. What's the gradient of this part of the graph? -2. What does a graph of y equals -2 look like? Straight line. So it would be a straight line at -2 up until the point 1, but it doesn't include 1. Done. All right, so this is the derivative function. This is f dash of x, part of it. So that's what the derivative of that graph looks like. What's the derivative of this part look like? 2x plus 2. What's 2x plus 2 look like? Well, it's got a y-intercept at 2 and it has a gradient of 2. So it's going up 2 and across 1. Up 2 and across 1. It's actually going to go something like that. Except we only want it from the point where x equals 1. Open circle. This is the second part of my gradient function. So, pink and green make up the original function f of x. The blue one makes up your two parts of your gradient function. I've just sketched the gradient. How did I do that? I know what a constant graph looks like. I know what a linear graph looks like. I know what a parabola looks like. I know what a linear graph looks like. I just do it in parts. Define when the derivative exists. Define the derivative function. Sketch the graph.